So we have this rigidly held tie bar and it's being heated, and what's happening here is this bar is trying to expand because it's heated and thermal expansion is taking place. But you can see right here where we have that system to the left and to the right that's representing a rigidly held structure. Now that is trying to prevent the system from expanding, and as a result it's causing stress to be induced. And what we're going to calculate here is the resultant stress that happens because it's trying to expand but the wall or the rigidly held structure is trying to push back. So let's go ahead and calculate the resultant stress. So of course, if we're going to calculate stress and we have this circular surface area or cross-sectional area, we have to find out what that area is. And I'm going to use pi times diameter squared divided by 4 for this one. So our diameter is 60 millimeters. So I'm going to just write that in meters as 0.06 squared. That's going to be divided by 4. So what we have here is a net result for our area of 2.83 multiplied by 10 to the power of negative 3, and that's in meters squared. So right there we have our area to begin with. Now the first stress that I'm going to calculate here is our direct stress, and our direct stress is going to be as a result of that 150 kilonewtons force that's happening, and that will be positive. So we'll have that 150 kilonewtons, so 150 times 10 to the power of 3, and then all divided by our area that we just got, which is 2.83 times 10 to the power of negative 3. So that gives us 53 megapascal for that direct stress. Now that we have the direct stress, what we're going to do is to find the compressive stress that is now induced thermally. So let's go ahead and find that thermal stress. So for thermal stress, we can use this equation, that's the Young's modulus or modulus of elasticity multiplied by our coefficient of thermal expansion and multiplied by our change in temperature. So we've been given these values in our question, and the modulus of elasticity, that's 200 gigapascal, so 200 multiplied by 10 to the power of 9, and our coefficient of thermal expansion there is 12 times 10 to the power of negative 6, and we have a change in temperature from 15 degrees Celsius to 50 degrees Celsius. So what we have to do is to subtract those two, so we'll end up with 50, take 15 for that one. And if we multiply out all of that, then that's going to give us our thermal stress, or in this instance, our compressive stress. So because it's compressive, I'm just going to add that negative there, negative, and that's now going to leave us with negative 84 megapascals. So remember, this is negative simply because it's stress going in a different direction. So what's happening now is we're going to find the resultant of these two stresses combined. So our resultant then stress of these two, and this will take place at the 180 degrees Celsius, is just the sum of these two stresses. So the direct stress summed with our thermal stress, and that leaves us with 53 megapascals minus our 84 megapascals, and that leaves us with a total of negative 31 megapascals, and that is representing our final stress. So that's the net effect of the stresses that's taking place on this system. So if you don't know how to calculate thermal expansion directly, then you should check this next video out, because it's a simple 3-minute video on how to calculate thermal expansion.